Imagine you run a 1 terabyte disk in the cloud. Tonight, only one tiny block of data changed. Must tomorrow's backup copy the entire terabyte again? That question is the whole reason Amazon EBS snapshots exist. An EBS volume is the virtual hard drive attached to an EC2 instance. It lives in a single availability zone. A snapshot is a point in time picture of that volume, a saved view of every written block at one exact moment. Here's the part that matters. The first snapshot really does copy everything currently written. Later snapshots do not. They only store what changed. You should now be able to see a snapshot as a marker on a timeline, not as a second full disk every time. And already one misconception falls away. A snapshot is not automatically a complete independent copy of the whole volume on every run. Before we open the blocks, notice where things live. Your EBS volume sits in one availability zone, one data center cluster inside a region. If that zone has trouble, the live volume can be unreachable. Snapshots are different. AWS stores them redundantly in Amazon S3, spread across the whole AWS region. That separation is deliberate. The working disk stays close to the instance for speed. The backup history is spread for durability and disaster recovery. So when you take a snapshot, you are not only freezing a moment in time, you are also moving a durable copy of that history out of the single zone that holds the volume. Keep that geography in mind. Every later choice about archive tiers, cross region copies, and sharing builds on it. Now watch the chain form, block by block. Picture a 15 gigabyte volume. In state 1, 10 gigabytes hold real data and the rest is empty. You take snapshot A. AWS copies those 10 written gigabytes. Snapshot A storage equals 10 gigabytes, a full initial backup of everything written. Time passes. 4 gigabytes of data change. The volume still shows 10 gigabytes of content, but 4 of them are new. You take snapshot B. AWS does not recopy the unchanged 6. It stores only the 4 changed gigabytes, and snapshot B keeps a reference back to the 6 gigabytes already held by snapshot A. Snapshot B's own storage is 4 gigabytes. Later, 2 more gigabytes change. Snapshot C stores those 2 and references the earlier blocks it still needs. Snapshot C storage is 2 gigabytes. Unchanged blocks are reused. Only new or changed blocks are written. You should now be able to follow the arrows and see why the second and third backups stay small, even though each one can rebuild the full volume state from that moment. Let's lock the storage math with the same 15 gigabyte volume from the guide. State 1 holds 10 gigabytes of real data. Snapshot A must store all 10. That is the initial backup. In state 2, 4 gigabytes change. The volume still presents about 10 gigabytes of content to the instance, but the snapshot system only needs to write the 4 gigabytes that differ. Snapshot B's billable storage is 4 gigabytes, while 6 gigabytes write along as references into snapshot A. In state 3, 2 gigabytes change. Snapshot C stores 2. Add the unique stored pieces, 10 plus 4 plus 2. The chain holds 16 gigabytes of physical snapshot data, yet it can rebuild 3 different points in time, including a full 10 gigabyte logical view from any of those markers. Compare that with 3 full independent copies, which would have been roughly 30 gigabytes. The savings compound as volumes grow and change rates stay modest. A 1 terabyte disk that changes 1% between backups adds about 10 gigabytes per snapshot after the first, not another terabyte. That is the economic heart of incremental snapshots. You should now be able to estimate chain storage as first full written size plus each later delta, not size times number of snapshots. Here is the clever part of a self-managing chain. Suppose you delete snapshot B. Does the 6 gigabyte block that B referenced disappear? No. Snapshot A still needs it, and snapshot C may still reference parts of the history through the chain. AWS removes only the blocks that are unique to the snapshot you deleted, blocks no other snapshot still points to. Shared blocks stay. That is why the guide calls these self-managing chains. Incremental does not mean earlier history vanishes when you add a new snapshot. It means storage is shared by reference. Delete carefully, and the system keeps every remaining point in time view intact. You should now be able to follow the chain and see why deleting one marker does not erase data still referenced elsewhere. Not every snapshot needs the same restore speed. AWS offers 3 ways to hold the same kind of chain, balancing cost against how fast you can come back. First, the standard tier. This is the default. Restores and boots happen in minutes. Use it for active, short-term backups you might need today. Second, EBS Snapshot Archive. Move older compliance snapshots into a colder vault. You can save up to 75% compared with keeping them in standard, but there is a contract, minimum retention of 90 days, and pulling a snapshot back to standard can take up to 24 hours. Third, Fast Snapshot Restore, or FSR. Normally, a freshly restored volume warms up as blocks are pulled from S3. FSR eliminates that initial warming latency. An FSR-enabled snapshot delivers maximum provisioned volume performance immediately. You should now be able to choose whether the priority is ordinary restore speed, low archival cost, or instant full performance. Slow down on the restore path because this is where Fast Snapshot Restore earns its name. When you create a volume from an ordinary snapshot, the volume becomes available quickly, but its blocks still live in S3 until something reads them. The first time an application touches a cold block, AWS pulls it down. That lazy loading is the warm-up. On a large volume, warm-up can mean uneven latency right when you are trying to recover. Standard tier is still the right default for most backups. Restores and boots in minutes are what you want for routine work. Archive is the opposite trade. You accept up to 24 hours to move a snapshot back to standard, in exchange for up to 75% lower storage cost and a 90-day minimum stay. FSR is the third trade. You enable it on a snapshot in a specific availability zone, and AWS prepares the data so a new volume starts at full provisioned performance with no S3 block pull delay. Use it when recovery time objectives are tight. A production database failover drill, for example, not on every nightly backup. You should now be able to match each tier to a sentence. Standard for everyday speed, archive for cold compliance history, FSR when the first second of performance matters as much as the last. Taking snapshots by hand does not scale. AWS Data Lifecycle Manager, or DLM, turns the chain into a policy. You tag the volumes you care about, for example, backup equals true. DLM watches for that tag. On an hourly, daily, or weekly schedule, it creates snapshots, retains them for the window you set, and deletes the ones that have expired. No manual cleanup drift. It can also copy snapshots to another AWS region automatically, so a region-wide outage does not erase your only history. Here is the misconception to drop. Automation is not only about creating backups on a timer. Retention, deletion, and geographic copies are part of the same rule system. You should now be able to see a backup policy as a set of rules that keeps the right history without you babysitting every snapshot. Geography deserves one more pass. Remember, the live EBS volume exists in a single availability zone. Snapshots already leave that zone and sit redundantly in S3 across the region. That protects you from a zone failure, but not from a full region event. Data Lifecycle Manager can close that gap. A policy can create the local snapshot on your schedule, retain it, and also copy it to a distant region automatically. The copy becomes a second chain you can turn into volumes where the original region cannot help you. Think of it as 3 concentric shields. The volume in one zone for performance, regional snapshots for zone disasters, and cross-region copies for region disasters. Tags like backup equals true decide which volumes enter the conveyor. Hourly, daily, or weekly cadences decide how fine the history is. Retention decides how far back you can travel. Deletion of expired snapshots keeps cost from drifting. You should now be able to draw those three shields and say which AWS feature builds each one. Sometimes the snapshot must leave your account. Sharing is allowed, but under strict guardrails. If the snapshot is unencrypted, an authorized account can create a new EBS volume directly from it. That is the simple path. If the snapshot is encrypted, sharing the snapshot alone is not enough. The owner must also share the custom AWS KMS key that encrypted it. Without the key, the recipient cannot use the data. And before the recipient modifies the snapshot or re-encrypts it, they must first copy it into their own account. A shared reference is not a local object they fully control. Two permissions travel together for encrypted data: permission on the snapshot and permission on the key. You should now be able to see that sharing the snapshot and sharing the key are separate decisions. Let's capture one by hand in the console so the idea becomes muscle memory. Open the EC2 dashboard. Under Elastic Block Store, choose Volumes. Select the volume you want to protect. You will see its volume ID, size, and type in the table. Open the Actions menu and choose Create Snapshot. On the Create form, give the snapshot a clear name and a short description of why it exists. Add optional tags if your team uses them for ownership or cost. Then confirm Create Snapshot. Nothing magical happens in that click except one thing. AWS begins freezing the current written blocks into the chain we already walked through. You should now be able to start the workflow from the volumes list without hunting the menu. Creation is asynchronous. Go to Snapshots under Elastic Block Store. Your new snapshot appears with status pending while blocks are gathered and stored. When the work finishes, the status becomes completed. Only then is the point-in-time view fully durable and ready to restore from. Do not treat pending as failure, and do not assume completed is instant on a large busy volume. Watch the status, confirm the name and volume ID match what you intended, and only then rely on it for recovery drills. You should now be able to reproduce the full console path and verify that the snapshot is ready before you walk away. Return to the opening puzzle. A 1 terabyte volume changed by one block. The answer is no. The next snapshot need not copy the terabyte again. Snapshots freeze a point in time. Later snapshots store only changes and keep references to shared blocks. Standard, archive, and fast snapshot restore let you trade restore speed for cost. Data Lifecycle Manager keeps the chain on schedule, deletes what expires, and can copy history across regions. Sharing moves a snapshot to another account only with the right permissions, and for encrypted data, the KMS key must travel too. Zoom out one level further. This is a practical lesson in storing history by reuse instead of duplication. The same idea behind incremental version control and many database backups. One open question to leave with: what other systems in your stack could keep many versions by storing only what changed? And who owns the policy that decides when those versions disappear?